Hi, good morning, Professor Mendel.
Good morning, Professor.
Wel- Welcome, sir, for this first session of day third. Within 10 minutes, we will start.
Sure, no problem. I'm ready.
Okay, sir. Okay, sir. Okay. I'll be back to you within 5-6 minutes. Professor Mandal, shall I proceed for the session?
Yeah, sure, no problem. I'm ready with
Okay.
my
Okay.
presentation.
Hello, everyone. I, Dr. Taimur Khan, coordinator for this event, welcome you all again to the third day of 1 week long ATAL FDP on Information and Communication Technologies for Smart City Applications, ICT4 Smart 2021, organized by Department of Electronics and Communication Engineering, NIT Silchar, and sponsored by AICT New Delhi under ATAL FDP scheme. I am delighted to have the first speaker, Professor Minal Kanti Mandal from IIT Kharagpur for this session. Dr. Mandal obtained BTech and MTech degrees from the Institute of Radio Physics and Electronics, University of Calcutta in 2001 and 2003 respectively, and PhD degree from the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur in 2008. From 2007 to 2009, he worked as a research fellow at the Institute for Infocom Research, Agency for Science, Technology and Research, A-Star Singapore. He also worked as a postdoctoral fellow at the Université de Quebec at Montreal from 2009 to 2010 and in the École Polytechnique de Montreal from 2010 to 2012. He joined IIT Kharagpur as a faculty of Department of Electronics and Electrical Communication Engineering in 2012, where he is presently serving as an associate professor. Dr. Mandal is a senior member of IEEE since 2013. He is in the editorial board of Wiley's International Journal of RF and Microwave Computer Aided Engineering. He was in the board of organizing committee member of several international conferences, including Asia Pacific Microwave Conference 2016. He obtained MHRD National Scholarship for Excellence in Secondary and Undergraduate Examination. He has authored or co-authored over 110 journals and conference papers, including 42 in different IEEE journals in the domain of microwave and millimeter wave circuits and systems. He has also filed 11 patents. His research interest includes co-design of active and passive components and their applications in reconfigurable antennas, millimeter wave imaging systems, beam forming network, Doppler radar, and 6-port receivers. Now, without any further delay, I welcome and invite you, Professor Mandal, to start the session.
Thank you, Professor Khan, for your nice introduction. So let me share my slide first.
Yes, yes, please.
So is it visible to you?
Yes, sir. Yes, sir. It is visible. And please proceed further.
Okay, very good morning to all of you. So my presentation will be on RF beamforming networks for 5G base stations. So mostly I am going to concentrate on the hardware aspect. So this is my presentation flow. After the introduction, we'll spend some time on the basics of wireless data transfer and phased array antennas. Then I'll discuss about the requirements for 5G base stations. And we already have several solutions. We can categorize them into two different domains: digital beamforming networks and RF analog beamforming networks. So I will present uh, that part. And then mostly I'm going to concentrate on the passive analog beamforming networks, focusing on time domain approach and frequency domain approach. And after that, I would also like to share some of our recent development in our group. So let me first start with some of our work which we are doing in last 3-4 years in IIT Kharagpur. So one of our research topic is Doppler radar, and we have already designed and implemented a series of Doppler radars. Here is one example. It is showing the RF part of a 2.4 gigahertz frequency modulated continuous wave radar circuit. So it was designed mostly for vibration measurement for different types of applications. So again, another Doppler radar, but this time it is at 24 gigahertz. Mostly it is using the ISM band at 24 gigahertz, which is 24 to 24.25 gigahertz. So it is a multi-purpose radar module. So top left circuit is showing the RF part, and microwave imaging system. So the very first example of imaging system which we designed, it is in 2017, and mostly by our master degree students under their master degree project work. So we developed all the components starting from array antennas, then mixer, low noise amplifier, detector, uh, and also two-axis antenna positioner. It is controllable by using a microcontroller or outdoor measurement. So mostly the scanning part, it is obtained by mechanically motor movement. So this is a photograph at microwave frequencies in the X band actually of our department. So you can see top left, it is the photograph at visible wavelength, and below it's showing the same at microwave frequencies. So we are first illuminating this by using a horn antenna in the X band by microwave signal, and then at the receiving end we are in one direction we are rotating the antenna. So basically we are using mechanical scanning, and in another direction we are using phase diary principle, and that's how we obtain this image. So this is our very first imaging system in microwave frequency range. And you can see here we have a metallic post. High reflection is coming out from the metal post. Here we have a tree. So power is mostly absorbed by the tree. So it is analyzing the reflected power. Now, at present, actually, we are developing a fully automated imaging system at 24 gigahertz ISM band. And the third research topic of interest, it is a 6-port receiver. So this name might be new to most of you. You know about homodyne receiver or super heterodyne receiver. In homodyne or super heterodyne receiver, we always use a mixer where we multiply two signals. It can be RF and LO or LO and IF in time domain. But here it is an all passive receiver, and we do not use multiplication in time domain. Rather, we use vector addition of RF signal in time domain. And since it is all passive component, so there is a possibility that we can design a receiver without any DC power source. So it can be an all passive configuration. So here an example in the X band again, and at the output side, we have 4 detectors connected to 4 output ports. One port is connected to LO, and the 6th port is connected to the incoming RF signal. And here is a measurement result where we transmitted bits of 1 and 0, and the received signal, it looks like this. So it is without any amplifier or signal processing. It is the raw data. So you can see the noise superimposed on 1 and 0. So again, it is mostly by our MTech students. Now, let us start our today's talk. 5th generation new radio, or 5G NR as popularly known. So this 5G, it has been already implemented in the developing countries, like in most of the European countries, in North America, in Southeast Asia, part of China and Japan. They are already in use, but with some limited capabilities. So they started since 2019. In fact, 5G handsets are available in those countries. And if we look at the market, so mostly they are from the companies like Qualcomm, Samsung, Huawei, then MediaTek, Intel, and Apple. And the base station supplier are mostly by Ericsson, Samsung, Nokia, and Huawei. But if we look at the systems which are already deployed, all of them, they are using sub 6 gigahertz band, 410 megahertz to 7125 megahertz bands, and different countries, they are using different frequency bands. So it did not converge. It is going through a transformation, and it is expected that it will converge finally in next 3 to 4 years, and that time it will be upgraded to millimeter wave frequency band. Now different companies, they are working actually separately, and all of them concentrating on different millimeter wave bands in the frequency range 24.25 gigahertz to 52.6 gigahertz. So for example, Qualcomm, they came up with a solution at 28 gigahertz. Now, if we look at the 5G base stations already existing in the developed countries, so this chart is available even in Wikipedia. So it is divided into different bands, and it is a full duplex communication systems. Some of them using frequency domain multiplexing, and some of them using time domain multiplexing. So the same receiving antenna, same antenna, it is being used for receiving as well as for transmitting. And the typical channel bandwidth, they are using 10 to 100 megahertz. In some of the countries, the channel bandwidths are 5 megahertz, 10 megahertz, 15 megahertz, 20 megahertz, and so on. So the expected data rate, it is the benchmark. It has been already set by International Telecommunication Unit. So it is 1 Gbps, and at least so that practically under any situation, at least it can support a data rate of 100 Mbps. So it is 10 to 100 times faster than the existing 4G network. Now, before coming to the next part of the requirements, let us discuss about some of the basics, some basic mathematical relationship. So the first example, most of us already learned in our UG class. It is the Phillips equation. So when we have a transmitting antenna and a receiving antenna separated by a distance of r, then the received power to transmitted power ratio, it depends on the gain of the antennas. So that include the base station antenna and the antenna of our handphone, the distance between the transmitter and receiver, and some other factors like SO11 or reflection coefficient of the antennas, then the polarization of the transmitted and receiving beam in their angle, and the atmospheric attenuation. So most importantly, we see, sorry, other than distance, it also depends on frequency. So if all other parameters are fixed, for a fixed distance, we need high power if we increase in frequency scale. So this is a basic requirement. So it dictates that you see in 3G or 4G base stations, power it is radiated almost on all the azimuth angle, covering whole 360 degree. Now we do not need this radiated power in all the direction. So it has to come to the user point. Now we can reduce this wastage by using beamforming. So we can have a very narrow beam coming out from the base station, and that's how we can reduce the wastage. Otherwise, at millimeter wave frequencies, actually the power requirement will go high. So right now, it is a few watts to tens of watts, the radiated power from this station. But if we do not follow this new configuration, then the requirement can be in kilowatt. So then it will create another problem of cost and design challenge. Further, if we can use beamforming and if we can direct energy to some specific direction, we can reuse the same frequency in other direction. So this it says that beamforming, it is becoming an important issue for 5G base stations. Second criteria is dictated by Shannon-Hartley theorem. It says the maximum channel capacity, it depends on the SNR, signal to noise ratio. So if we look at the different digital modulation scheme, we see that bit error rate, it is related to different modulation scheme. So in digital modulation, we know that we can modulate the amplitude, and that's how we can get amplitude shift keying. So for this first example, let's say 1, it is being transmitted when the signal is present, and 0 is transmitted when no signal is present. It is amplitude shift keying. Now we can also send digital information 1 and 0s by changing the frequency. Then it is called FSK. We can do the same thing by changing the phase. Then we call it PSK. So one of the popular modulation schemes is quadrature amplitude modulation, CAM signal. So where we change both amplitude as well as the phase of transmitted signal. Now, for wireless data communication, the bit error rate, it is specified as 10 to the power minus 5, and for wired communication it is 10 to the power minus 8. Now if I consider 10 to the bit error probability of 10 to the power minus 5, what we see that ASK, it requires to maintain maximum SNR, whereas compared to ASK or FSK, BPSK and QPSK, it requires minimum SNR. So modulation scheme is also an important factor. Otherwise, for the same distance, for the same data rate, we need to maintain different level of SNR. Then from this chart, what we can see that for QPSK or BPSK, it might require lower transmitted power compared to ASK or FSK. So bandwidth efficiency, another important term. So if I have 5 megahertz channel, then the channel capacity or or the data rate, it can be theoretically infinite, only limited by SNR. So if we look at both bandwidth efficiency and the SNR requirement, it seems that quadrature amplitude modulation is the best scheme, and that is why for Wi-Fi we use this quadrature amplitude modulation. Now coming to 5th generation new radio base station requirement. So there are many differences, and that dictates actually the technological approach between 4G and 5G. For example, in 4G, if we consider one user equipment which is communicating to 3 base stations, and the distances are shown as D1, D2, and D3. So here the user distance, it is it is calculated by the time delay and received power level. So accuracy is very poor, of the order of 10 meter. But for 5G, this accuracy, it is expected it will improve to at least 1 meter, and that will be done by using beamforming algorithm and calculating the angle of arrival. So for in the first example, we are considering only the magnitude or amplitude part of the received signal, but for the second example, we are considering phase as well as amplitude. So here the signal is represented by a vector signal. Further, it is expected that many IoT terminals will be connected to base stations, so we'll be having extra loading. So power delivery and management of radiated power, it is becoming an important issue. And it is suggested, people already working on it, that this power management will be done by using artificial intelligence. Well, some other requirements. Now we need to deploy these base stations in different scenario. It can be urban or rural scenario, and they require different criteria. For example, in the rural region, mostly we are dealing with low-rise building, and that's why we need to scan or steer the beam in mostly azimuth plane. We do not need as such anything in horizontal plane, sorry, in vertical plane. So but in city the situation is different. We need to deal with some of the high rises also, so then we need both beam steering in vertical direction as well as in horizontal direction. Now consider a different situation. Let's say the base station is communicating to one user equipment, and user equipment is traveling in a car on a highway. Then the beam, it should follow the car. So we see that we have different requirements for 5G base stations. Now, if I compare this with that for 3G or 4G, which is already existing, for 3G and 4G base station antennas, typically they have a 3 dB beam width of 65° or 90° or 33°. Now, depending on application scenario, they choose any of the antennas from these three different examples. But for 5G, we do not have a fixed beam. So the 5G base stations already deployed, they are limited in capability in the sense that right now, at present, they are using fixed beam antennas, but with multiple beams. But in the upcoming 5G, it is going through continuous upgradation. So it is expected that all these features will be included in the base station antenna systems. Now, for let's say one user, he's moving away from the base station. Now, when he's moving away from base station, then we need to transmit more power since R is increasing to maintain the minimum SNR value. So then along with beam steering, we also need to change the beam width. That is another criteria and another burden coming here. Similarly, let's say R is fixed, but angle is changing. So that highway example. So in that case, we need to steer the beam. Now we have, let's say, both of these two situations. R is changing as well as theta is changing. So we need a complete control over the beam. We should be able to steer the beam as well as we should be able to tune the beam width, 3 dB beam width. So all these features, it is expected that they will be included in the base station antenna array system, and that's why people are talking about MIMO antennas, particularly massive MIMO antennas. And the array antenna, it is at least 16 by 16 or of the order of 32 by 32. It's huge, and it is able to communicate with multiple users at the same time. Now, if the beam width is very narrow, then we can reuse the beam in other direction. So here is an example. So these, let's say at the same frequencies and for the same channel, we are communicating with user equipment one in this direction. Then using the same specification, we can radiate it in the direction of user equipment two. But considering practical situation, no antenna radiates power only in one direction. It has side lobes, back lobes, and other issues. But when we want to reuse the same frequency component, we should make sure that this antenna it should provide a null direction in the direction of UE2. Same thing is true for UE2. So that corresponding set of antennas, it should provide another null in UE1. Now, if users they are moving, let's say with time, then the beam it should have also null steering capability. So not only then the beam steering, we also need null steering capability included in the array antenna itself. So analysis of array antenna, its implementation, it is becoming one of the very important issue. High precision beamforming, then it is mandatory for accurate coverage, and for that we need some beamforming algorithm. So to implement this type of features, then we need coordination at different levels. We need coordination at component level, coordination at product level, and coordination at feature level. So at component level, the final aim is to obtain all these basic features of array antennas, then array vector, and the phase difference among the elements. So how accurately we can implement that is becoming an important issue, which is not present right now at the deployed 5G base stations. So if we look at that, then not only the antenna, the other RF components connected to antenna, such as low noise amplifier for the receiver, power amplifier for the transmitter, mixer, phase shifter, attenuator, and the gain control unit. So all of them, they are actually nonlinear elements. So when we are going to design them and then finally connecting them to realize this system, then it is becoming a challenging issue, and we have to be very careful when going for component level coordination. So similarly, we also need coordination at product level. So in the product level, we have actually passive part as well as active parts, and we also have the high frequency RF part, and after mixer it is low frequency. Then we are digitizing the signal using ADC and DAC, then the signal processing. So all of them comes at the product level, and in addition to that, we also doing feature level coordination. So at the feature level means reuse of different frequency bands, then calibration of the channel. So these things are coming at the feature level. So all of these then is becoming important. Now looking at the base station antennas, then array synthesis and beamforming networks and the corresponding algorithm, it is becoming an important issue. So let us move to the next part then, and how we can control any beam. So basic phased array, it is in the RF domain at RF frequency range. So we know that, let's say if we have a linear array antenna as shown here with n number of radiating elements. Now if we introduce some phase shift, let's say progressive phase shift of delta phi, then the beam direction theta, it depends on this phase shift delta phi. So this basic array principle, it came just after First World War, and previously until 1950s or 60s, people used only mechanical scanning by using some motor. But after that, electronic scanning was introduced. So where we can change delta phi as well as the signal amplitude. So signal, it is distributed over n number of elements. Now for array synthesis, we need to control both the delta phi progressive phase change as well as the signal distribution, its amplitude distribution over the array. So it is in electronically, it is done by using RF phase shifter. Now, when we use RF phase shifter, we can have time domain approach, we may have frequency domain approach. So I'm giving one example. Let's say this is a simplified version of two element array. Now the beam direction is theta. Now, if we look at this figure, let's say these antennas, they are working as transmitting antenna. Then the left antenna on the left, it should radiate delta t time before the second antenna. Then we can have a beam angle of theta. So actual relationship, it is coming from time domain, and it is given by delta t equal to d sine theta by c. In the receiving mode, it will be just opposite, in opposite direction. So we should have, instead of delta phi, then we should apply some time difference among the array elements. Otherwise, we'll face a problem like this as shown here, because we know that theta equal to omega t. Now, if I fix theta, then if we change frequency, then the corresponding time delay will change. So let's say if I designed one array antenna with phase shifting principle, then if I change the operating frequency from 10 gigahertz to 9 gigahertz, so in this case, this array is designed to have theta at 30 degree. Now, and this design is implemented at 10 gigahertz. Now, if I change the operating frequency from 10 to 9 or 10 to 11, beam position is changing. So we have beam spreading effect for this. So this is not an accurate method. But instead, if we use time delay approach, and if we apply progressive time delay among the element, then what we see that it is becoming independent of operating frequency. So at 9, 10, or 11 gigahertz, the beam is pointed only at 30-degree direction. Now we can tune delta t to have beam in different direction. Next, the beam formats. Now here we have for actually communication in two directions, from the transmitter and for the receiver, we have power flow in two different directions. For a transmitting part, the antenna, it is followed by power amplifier, and for the receiving section, it is followed by low noise amplifier. Now, if we can have a high frequency DAC or ADC, then just after low noise amplifier, we can directly digitize the signal, and we can, once it is digitized, then it will come to computer and we have full control over it. So in once the signal it is in digital domain, then I can control it from signal processing unit. So we do not need any other RF component like mixer or phase shifter. So this is called software defined radio, but it has a problem. High speed DAC and ADC, it is very expensive. So in fact, above X band, it is not available in market. So we cannot have a software defined radio at millimeter wave frequencies, at least with the present technology. Then what is the solution for beamforming? Then we can have either digital beamforming network or analog beamforming network. So I'm coming to this point one by one. So the first example, it shows the digital beamforming network using TR module, transmit receive module, or popularly known as TR module. So inside a TR module, you can see that it contains two paths. In transmitting path, after the mixer, so mixer is up converting from IF, then we have an attenuator to adjust the amplitude, and it is followed by a series of amplifier, and the last stage is a power amplifier and connected to antenna by using a SPDT switch. Now in the receiving part, antenna it is followed by LNA and series of amplifiers, again a gain control unit, and then it is down converted by the mixer. And after this TR module, we have ADC or DAC, depending on it is transmitting or receiving. So here we do not have the problem of requirement of high speed ADC or DAC unit. So once it is down converted, it can be at megahertz frequencies, and we can easily use ADC and DAC directly. We can digitize the signal, and then we can control it from our computer or signal processing unit. So we can use a very basic relationship. In the mixer, we are multiplying two signals. Let's say the the LO signal and the IF signal, and we are up converting it for the transmitter part. Now we have a simple relationship cos A into cos B. So if I introduce some phase shift from my computer with the IF, so after up conversion, that phase shift, it will be there. It will retain that RF frequency, it will, or the signal component, it will retain that phase shift introduced by the computer. So this is the basic logic. Then I can control the amplitude as well as phase shifting from the computer directly in digital domain. So that is how it is done for the digital beamforming network. But here we have an issue. Each radiating element, it should be connected to. So if we have one n by n array antenna, then we need n by n numbers of TR module as well as n by n numbers of DAC and ADC. So if the cost of a single TR module it is high, then the cost of the whole module, array module, it is becoming high. Otherwise, since we have digital control, even after implementing the system, we can configure it. So that is the main advantage of digital beamforming network. But looking at the current available technological option, we see that below 5 gigahertz it may be feasible, but at millimeter wave frequencies right now it is really challenging. How to keep overall cost low? Because at millimeter wave frequencies, TR module itself it is very expensive. And now if we add n by n TR modules and n by n ADC DAC, of course the system cost will be very high. Now in RF domain, what is done? In RF domain, this phase shifting or amplitude distribution, it is controlled at microwave frequencies or millimeter wave frequencies directly. So this phase shifting unit or the amplitude control part, it sits after the mixer. So between mixer and antenna. So we need RF phase shifter. And from the signal processing unit, it nothing has to do with the phase shifter. So phase shifter is controlled by using a different signal processing unit, and that's how we can have or we can implement different algorithms. We can have good control over the amplitude distribution as well as phase distribution. So now millimeter wave phase shifters, they are available in market, but they are power hungry, but it is implementable, and compared to TR modules at millimeter wave frequencies, it is cheaper. So then these are the technological options already we have in market. So what can be the ideal solution? So once this TR module cost it goes down, it seems that digital beamforming network it is the ideal solution. But what is possible at present scenario? So we can take the advantage of both digital beamforming network and the analog beamforming network. So people using sub-array concept. So in one sub-array, they will be using analog beamforming networks, and then it is controlled by using a digital beamforming network. And the approach is called hybrid beamforming networks. So this is now a hot topic. So in near future, at least in the coming years, it is expected that all of the base stations, they will be using hybrid beamforming approach. So this is just the main points of advantage and disadvantages of digital beamforming network and analog beamforming network. So for digital beamformers, then beam steering is possible without any microwave component. But this is called the software defined radio. But right now, it is not possible at microwave frequencies since we do not have low cost ADC DAC at gigahertz frequencies. Then the alternative approach that we need to use TR module with each of the radiating elements, and then we can use a mixer to down convert the signal from gigahertz to megahertz, and after that we can use ADC or DAC for digital control. So since the signal is available directly in digital domain, then direct signal processing is possible from a computer. So adaptive beamforming is possible. So it has the advantage of easy calibration of the array and array front end in digital domain. Further, we have a provision of on-the-fly reconfiguration. So even after implementation, we can change or the algorithm itself. But of course, it has some disadvantages. Cost is one of them. Then it may require high RF power. It depends on implementation scheme. And at higher frequencies, particularly at millimeter wave frequencies and terahertz frequencies, right now we do not have any solution for that. Analog beamformer compared to digital beamformers, they are of low cost, less complex at higher microwave frequencies or even at millimeter wave frequencies. And if we look at the available technologies, frequency domain approach as well as time domain approach, they are available. We can have beam switching as well as continuous scanning. So in the beam switching, particularly, mostly they use some traditional method based on completely passive microwave components. So this is one of the advantages, completely passive microwave components. So examples are Rotman lens, Butler matrix, Nolan matrix, etc. Disadvantage, high power loss in the phase shifter. If we use particularly ferrite phase shifter, they are power hungry and bulky for finer resolution. But when we look at the base station requirements, weight is not a problem as such. We do not have to carry it. It's not mobile. So then, as I said, the present approach is to utilize the advantages of these both approaches, digital beamforming network and the analog beamforming network, and people going for hybrid approach using sub-array concept. Next, let me show some of our components developed at IIT Kharagpur. So all of these are published in IEEE, different IEEE transactions. So if you are interested for any design, you can go through these papers. The references are listed here. Originally, we developed these components for different radar applications, but they can be also frequency scaled to 5G band and using the same design approach and design method. So design guidelines, it's given in the corresponding papers. So the very first example, it is a switchable time delay line using open stubs. So here, if you look at the geometry carefully, we are using open stubs, many of them, and open stub, they are connected to a host microstrip line and by using a switch. These white color SMT components, it is actually the inductors used for biasing. And now if you look at the result here, delay versus frequency, it is a very wideband design. It works over 1 to 4 gigahertz, and we can use a computer or signal processing unit to control the switching position or the bits, and that's how we can have different time delay values. So we can use this type of delay lines for controlling the beam position. Another example, more or less the concept is very similar to the first one, but here instead of one single open stub, we are using a stepped impedance stub. So this is the first section of the stepped impedance, and it is wider, so it is having lower characteristics impedance implemented in microstrip line technology. And other open stubs, they are connected to this first stub by using pin diode switches. So again, these black dots, they are actually pin switches, and this white color, they are the inductors. So now we can change the switching configuration, and we can have actually different delay levels. This is a third example. This is implementation of a SPST switch using pin diode. So here you can see these are the SMP connectors, and this switch is designed at 24 gigahertz. So our main contribution was how to compensate the effect of parasitic and how we can improve the switching performance. So basically the switching speed as well as insertion loss when the switch is on, and how to improve rejection when the switch is off. So mostly at higher frequencies, these values decreases because of the pin parasitic. And here we tried to improve it, and we described some methods to nullify the effect of the parasitics. And that's how this is one fabrication example. Here you can see that using a single pin diode, we can have a rejection of 30 dB, whereas insertion loss, it is of the order of 2 to 3 dB. Some other examples, these are delay line with simultaneous control of slope and peak. So this type of delay line is used in analog signal processing in real time. So here actually this is the first element which was published in MTT December 2019 issue, where we can control both the peak value of delay as well as its width. So in the first example, in this measurement result, I'm showing that delay bandwidth, it is tuned, whereas the peak value is fixed at 2.5 gigahertz. And in the second example, the peak value, it is being changed without changing the frequency spreading. So same design. In this third example, sorry, in the second example, it is a reflection type phase shifter. So a reflection type phase shifter, it can provide phase tuning over a very wide phase range. So here, if you look at the measured phase response, so in the circuit, actually, we are using a modified quadrature hybrid coupler, and then one open stub, and two varactor diodes are connected at two arms. Now we can control the capacitance of each varactor diode, and that's how we can actually tune the load as seen at this port and at this port. Then accordingly, the reflected signal from the load, it will change, and the incident and this reflected signal, they superimpose to have one interference pattern. Together, it provides a phase shift from port 1 to port 2 with respect to some reference line. Now, if we look at the values, so phase tuning over a range of 0 to 360 degree is possible. So it is not possible for a conventional phase shifter to obtain such a wide range variation of phase shifting. So if we look at the first part at least 9 to 10 gigahertz, then the phase shift it remains more or less same. It is not changing with frequency. Anyway, we can use some sort of calibration with this. Now, as I said that we'll be focusing mostly on the passive analog beamforming network. So these are some of the old and traditional technology, and but they are still in use. Now people actually revisiting these old technologies and checking that if we can integrate them with the digital beamforming network by using the hybrid beamforming approaches. So we have two approaches, time domain approach and frequency domain approach. In the time domain approach, it uses length principle. So delay by a propagating signal, providing over a given length of propagation. So examples are Rotman lengths, Rouge lengths, and in frequency domain approach, examples are Butler matrix, Blast matrix, Nolan matrix, and so on. So let me show one example from this category, time domain and frequency domain category. So this is the first example, Rotman length. It uses simply optical principle. As you can see here, we have a feed plane, or maybe it is more clear from this figure. We have a feed plane. So transmission lines are connected to this feed plane, and we can connect the RF source to one of the feed lines at a given time. And at the output side, this is the lens curve, and after that we have some delay lines, and the antennas they are connected to the output ports. So when the signal is fed at, let's say, the point f1, then it propagates throughout the lens as shown here. In this example, we are feeding at port 1, that is RF source is connected to port 1. Then signal it comes inside this. Inside here it is the parallel plate mode. So it is realized in microstrip line technology. And if you look at this bottom figure, it's showing the metal part in the top layer, and bottom side we have the ground plane. So input fit lines, these are microstrip line. Output lines, they are also in microstrip line technology. So now this signal propagates and it spreads throughout the lens. And if we look at the output ports, this signal it is distributed over the n j number of output ports with a progressive phase change. Now, if I connect to port 2, then again signal is distributed over the output ports, but this time with a different phase relationship. So the propagation delay, it is different from port 1 to the output port and from port 2 to the output ports. Now, if we need some further delay adjustment, that can be done from outside by using different length of transmission line. So if we use different length of transmission line, then they will provide different delays for the signal. Now, as I said that antennas, they are connected to these output ports. So depending on the required delay, then we can switch among the input ports. So we need a high pole switch to connect the RF signal to the input ports. So the basic principle, it is based on time delay, and here we can have multiple beams simultaneously. Now, from frequency domain, this is an example of a Butler matrix. So Butler matrix, it always has a order of 2 to the power n by 2 to the power n. 2 to the power n is the number of input ports. It is also having the same number of output ports. So here, this figure, it shows a 4 by 4 Butler matrix. So we have 4 input ports and 4 output ports. Now RF signal at a time, it is connected to one of the input ports. Now inside the matrix, we have mostly the passive components. Here we have 4 90-degree branch line coupler and 2 45-degree phase shifter and 2 crossover. So number of branch line coupler or number of phase shifter requirement, it increases with the order of the Butler matrix. Then when we connect to port 1, then the phase difference, progressive phase difference is 45-degree. When we connect to port 2, then the progressive phase difference is minus 135-degree and so on. So that means if I connect RF signal to port 1, then we have a beam position. Let's say this one. Now, if I connect to port 2, since the progressive phase difference is changing, we have now a different beam position. Let's say this beam. So that's how for a 4 by 4 Butler matrix, we have 4 distinct beam positions. If we want to increase the resolution, then we have to go to higher order Butler matrix. So in general, for a n by n Butler matrix, the PF beam location is given by this relationship, where D, it is the element to element spacing. So antennas, they are connected to these output ports. So here we can connect 4 antennas. Now, if we need 64 beam position, then we have to use a 64 by 64 Butler matrix. So you can imagine how many passive components it requires. So that is why for very high resolution application, we do not, we try to avoid Butler matrix. But here our main target is to use a combined approach, a hybrid approach. So then we can use a lower order Butler matrix, and that we can integrate with digital beamforming using sub-array concept. So here is an implementation example in PCB technology using substrate integrated waveguide. So you can see the port 1 to port 4. These are the input feed ports, and port 5 to port 8. These are the output ports where antennas are connected. And it works, this is in SIW, it works like a rectangular waveguide. So this signal, when fed to port 1, then the first component, this is actually a coupler, and the phase shifting, it is realized by length difference. So 45-degree, we need additional 45-degree phase for these two extreme arms, and that is realized by this line and by this line. Their lengths are little longer, and the middle part, it is a crossover as shown here. So when I feed at port 1, then the signal, it's coming to this side. So from here, the signal will come to this point. So I'm showing here one example. We developed a new Butler matrix by modifying its internal configuration. So the basic logic is that how to improve resolution of a lower order Butler matrix. So we use a simple concept that, let's say, for a 4 by 4 Butler matrix, the beam positions are fixed. Now, if we can steer the beam further, then we can cover this whole half of this azimuth plane, plus 90 to minus 90 degree. But what is the advantage over a traditional phase shifting approach? The advantage is that already we have a fixed beam position, then the beam steering range, it is much less, 1 by 4, compared to a traditional RF phase shifting approach, where one beam we need to change from plus 90 to minus 90. Then the required tuning range of phase shifter, it is much higher. So we tried to utilize this in the Butler matrix itself. So in that case, what we see that the phase shifting element, which was 45 degree for a 4 by 4 Butler matrix. Now we have generalized it for a n by n Butler matrix. Then what will be the phase shifting requirement? So we are just introducing a tunable phase shifter at the location of this fixed phase shifting unit. Otherwise, we are not changing the basic Butler matrix. So quadrature hybrid coupler, their position, then the crossover, it remains same. So just this phase shifting unit, instead of a fixed phase shifting, we are using a tunable phase shifting. Now we have two different approaches. In one approach, we used a length of transmission line to change the phase. So for a length of transmission line L, theta phase shift is given by beta into L. Beta is 2 pi by lambda g. So if I change the frequency for a fixed length of transmission line, then the corresponding theta will change. So here, the same 4 by 4 Butler matrix, but for wideband design, instead of one single branch line coupler, we used two section branch line coupler, and then the required phase shifting, it is calculated. So this paper not yet published, but it has been applied for a patent for this configuration. So the design equations are given. Let's say we want to scan this whole range plus 90 to minus 90 over a given frequency band by changing the frequency from F1 to F2. Then what should be the required phase variation? And from that, we can calculate what should be the change in length. So that additional length, it is implemented here, but this length, it is not for a fixed phase shifting. It has a relationship with the time, using the relationship theta equal to beta into L. So as we, let's say now, we are fitting at port P1 and changing the operating frequency from F1 to F2, then this beam at the output side, it will scan over the from this point to from this point to this point. So that's how for port 2, again from this point to this point, and so on. So that's how we can cover plus minus 90-degree range. Now in most of the applications, actually, if we change frequency, just like this wireless communication, we cannot change carrier frequency. So for imaging applications and other radar applications, we can use this approach. But for wireless communication, it won't work. So frequency we cannot change at will. But we can change the implementation scheme. So in that case, what we did, instead of that delay line, we use that reflection type phase shifter we developed earlier. So in place of the fixed 45-degree change of phase, we now introduce reflection type phase shifter. So you can see here one top and one below here, and at the output side we need two more here, phi n1 and phi n2, and together we need four of them, and they are providing the required phase. So we can tune the phase electronically by changing the varactor biasing. Now it is not the same as the original Butler matrix. So here you see the beam position is fixed for 45 degree. Now if I change 45 degree to some other value arbitrarily, let's say 50 degree or 60 degree, this progressive phase shift relationship will not be maintained. It will change completely. So what I mean, from 5 to 6, now it is for plus 45 degree. From 6 to 7, it is plus 45 degree. So progressive phase shift remains constant. But if I change from 45 degree to some other value arbitrarily, then 5 to 6 and 6 to 7 phase difference will be different. So it cannot be done arbitrarily. First, we need to solve the Butler matrix and find out relationship, and then actually we have to control accordingly. So that has been done here actually. I'm not going through the derivation. So after realizing, then I'm showing here the beam steering capability for different input switching position. So when port 4 is connected to RF source, so after that, then we are tuning the varactor voltage, and then you can see that beam steering capability. So that's how it can cover all the blind spots. In the second example, we are feeding now at port 2 of the input side, and then we are showing the beam steering capability. But we have an issue with the amplitude. It is a common thing for any phased array antennas. So another example is Nolan matrix. In this case, this port 1 to port N, these are the input ports, and port A1 to AN, these are the output ports. So all the radiating element, they are connected to port A1 to port AN. Now, when we feed at port 1, so here we have a coupler unit. So it divides the power into two parts. One part goes to AN and the remaining part comes here. Then we have a phase shifting element. So it changes the phase, and after that the same thing is repeated. So when we feed basically from port 1, then we have a amplitude distribution from array antenna element AN to A1, and the phase distribution, it is maintained by these phase shifters. Similarly, for port 2, these are the phase shifters and the power dividers. So again, we have a relationship. What should be the value of phi 1, phi 1, 1, 1, 2, 1, 3, similarly 2, 1, 3, 1, and so on. So it is basically a matrix and called as the Nolan matrix by the name of the inventor. So for a Nolan matrix, number of elements are more compared to Butler matrix. So that is why it is not so popular. And we also need a power division which is not equal power division. So that is also sometimes challenging, particularly when we go for higher order. Now, what we did, we designed a coupler with arbitrary phase shifting and arbitrary amplitude ratio capability. So for a traditional Nolan matrix, you can see we have the power dividers as well as external phase shifting unit. Now we replace them by a coupler which can take part in phase shifting as well. So we do not need phase shifting unit, additional phase shifting unit which is outside of the power divider. So these are the modified coupling unit C1 to C6. So that's how actually we can decrease the number of elements. So here is the example. So this unit is the basic coupling unit with arbitrary phase, arbitrary coupling ability, and the design equations are given here. And again, it is a published paper in IET, June 2019. And you can see that this is an example of a 4 by 4 Nolan matrix. Port 1 to port 4, these are the input ports, and port 5 to port 8, these are the output ports. And here we have the couplers, and this is not the conventional coupler actually. So we do not need any additional phase shifting unit. So that phase shifter, it has been absorbed inside the coupler. So I want to show one more example. So this, it has been patented, and also it is published in IEEE tab in May 2020 issue. So this is an example of an array antenna where, without using any beamforming unit, directly we can control beam position as well as beam width. So the basic principle is based on leaky wave antenna principle. If you look at this implementation scheme, this is the photographs, top view and bottom view. So in the ground plane, we have CSRR, so complementary split ring resonator. And in the top plane, we have some open stub, then a gap, open stub, then again a gap. Now we used pin diodes for switching. So one set of pin diode connected to this open stub, and another set which is placed on the gaps. So the second set which are placed on the gap, we use the pin diodes as variable register at microwave frequencies. So if I change the current flowing through pin diode, then the corresponding resistance will change. So we can have control over alpha, radiation constant. So that's how we can control the beam width. Now, at first sight, it looks like pin diode we are using as a resistance in series, it will introduce loss. But EM analysis, it shows the current component flowing through the pin diode, it's very small. As such, it does not provide any loss. So most of the power, it is being radiated. But at the same time, we have a very good control over the attenuation constant alpha. And the beam position, it is by using open stub. So open stub end, when they are switched on or off, then the corresponding capacitance loading, it changes. Capacitance loading to the microstrip line. So that means we can control beta, and beta determines the scan angle or beam position for any leaky wave antenna. So for this configuration, then at a fixed frequency, we can tune alpha as well as we can tune beta. So that's how we have good control over beam steering as well as beam width tuning. So the advantage, another advantage is that almost no change of gain value over steering angle. So these are showing some represented by 4-pin diode. So in the first example, all the switching states, they are 0, 0. And the last example, all the switching states are 1, 1. So these are the two extreme beam positions. Anyway, so now let us conclude. So basically, in last 1 hour, it was just an introduction to beamforming networks and what is the requirement for the upcoming base stations for 5G. Now, from the discussions, it seems that analog beamforming networks are of low cost and they are easy to implement, and they can be made competitive with digital beamforming networks with some innovative approaches. So for example, I have shown an example for branch line, Butler matrix, which we developed for fixed frequency beam tuning. But looking at the available options, at least available commercially, it seems that the best solution is hybrid beamformers, which uses the sub-array concept and the principle of digital beamformers as well as the analog beamformers. And finally, I would like to also acknowledge, so all the examples, whatever I have shown here, so mostly they are by my PhD students. So Dr. Avinash Singh, Dr. Joydev Mondal, and Robisha, and other MTech students. Yeah. So thank you for your attention. So if you have any question, so you are free to ask. You can switch on your microphone. Thank you.
Uh, Thank you, Professor Mandal, for a wonderful talk and practical implemented research on 5G base station. I am looking into the chat box of YouTube channel to find out the queries, but as such, there is no like effective query which should be shared here. Anyway, later on, if participants are having any query or wants to discuss something more in detail, I request them to contact you directly through mail or through some other uh, social media platform. With this one, thank you, Professor Mandal, for sparing your valuable times with us in delivering this talk. And
It was my pleasure.
prior to that, accepting our invitation to, with in the same continuation, I am inviting you for attending the valedictory session 2, which is scheduled on 15th January 3:30 p.m. onward. We will be happy to see you in the valedictory session. With this, thank you very much once again. Please.
Yeah, thank you, Professor Khan. So it was my pleasure actually. And thanks to all the participants and organizers.
Okay, sir. Thank you very much.
So if you have any question, I have already shared my email ID in the last slide.
Yes,
You please feel free to contact me anytime.
sure, sir.
Again, thank you all. Bye.
Okay. Okay, sir. Bye. Dear participant, next session will be started at 11 o'clock. Uh, After 10 minutes, we will start second lecture of the day third session.
Hello, Taimur.
Hi, Dr. Sudhakar Modem.
Hi, sir. How are you?
Good morning. How are you?
Good morning. Good morning, sir. How are you? I'm good. How are the things today?
Good, good. Everything is good here.
Yes, sir.
Uh, Okay. I think you are out from your institute,
Yes,
outside.
yes, sir.
Okay,
Yeah,
okay,
I'm outside institute, so I'm at IIT Delhi for
okay, okay, okay.
yeah
Good.
some other work. Yeah.
Okay.
Yes, sir.
Shall I proceed for second session?
Let me check whether screen sharing is. I just check it.
No,
It is.
later on, we will invite you
Yeah.
for sharing the
Yeah.
screen.
Yes, yes.
Okay, okay. Uh, I am delighted to have next is invited speaker, Dr. Sudhakar Modem from IIT Jammu. Dr. Sudhakar is working as an assistant professor in the electrical engineering department at Indian Institute of Technology, Jammu, from May 2019. His specialization is in communication engineering, and his research interests include IoT networks, RF energy harvesting, cognitive radio network, and image processing. He has published his research contribution in IEEE transaction on communication, IEEE transactions on vehicular technologies, IEEE system journal, IEEE communication letters, and IET transaction on image processing. He applied for an Indian as well as US patent on RF energy harvesting for a lifetime maximization. Before joining IIT Jammu, he has worked at IIIT Dharwad and MITS Gwalior. He received his PhD degree in communication engineering from IIT Delhi in February 2018 and MTech degree in communication and signal processing from IIT Hyderabad in 2012. He is currently working towards a smart agriculture and electrical vehicles with SCRB funding. Now, I request and invite Dr. Morden to start the session.
Good morning, all. So let me share my screen. Is it my screen visible?
Yeah, it is visible.
Yes. Yeah.
Okay. Yeah. You hide this icon on bottom side one. Yes, yes, please.
Yes. Yes. Yeah.
Okay, okay,
Thank you.
okay. Please go ahead.
So good morning, all. So I'm Dr. Sudhakar. I'm working as assistant professor at IIT Jammu. Today I'm going to present self-sustainable IoT solutions for smart applications as part of ATAL FDP on information and communication technologies for smart city applications. So as we are saying, our basic focus is on IoT. So what is IoT basically? IoT is nothing but connecting of different services and devices to the internet so that we can monitor, analyze, and take the decision from remote locations. So the applications are varied from smart cities, smart agriculture, autonomous vehicles, smart grids, smart healthcare, etc. So when these all applications come into the existence, there will be billions and billions of devices will be there. So in order to support billions and billions of devices, we need a platform so which can support these services. So 5G is one of that solution which will support this much extent of uh, data volumes and number of devices as well as the data speeds, and it offers the very low latency, and it is expected that the 5G devices should be of 10 years lifetime, so as per the standards. So if you when you are going to the 5G, the transmission range will become very less because we are using the higher frequencies. So if you are using lower frequencies, the penetration depth is large. So when you are using the higher frequencies, the range will be shortened. So when you want to offer for long range communication, we need a relay. So relays improves the coverage and reliability, and it is standardized in IEEE standard 802.16J in 2009, and it is also standardized in LTE. So when the relay, what is relay? Relay is basically, it supports the communication between the source and the destination. So it will be placed in the in between, and it will support the communication between the source and the destination. So in order to support that communication, it has to expand its own battery energy to support the communication of others. So which is not expected. If IoT device is expected to be higher lifetime, the energy consumption should be very minimized. So this lifetime requirement can be achieved only by using the energy harvesting or hybrid. That means harvest energy plus existing battery energy. So some of the 5G key technologies are such as relaying networks, energy harvesting networks, and spectral efficient protocols. These are the technologies which will fulfill the requirements of 5G. So in this talk, we are basically focusing on energy harvesting at the IoT nodes and spectral efficient protocols, which can be improve the spectrum efficiency. So what is mean by energy harvesting? Energy harvesting is nothing but converting the ambient energy to the our usable electrical energy. It can be harvested from the different sources such as solar, wind, vibrations, and all these things. But the main problem with these natural resource sources are the solar will not exist all time because it is existing only in daytime, and it will not be there in nighttime. And similarly, it cannot be available on places, all places such as snow places and all these things. It will not be available for much. Similarly, wind and vibration has its own limitations. So it is proved that harvesting energy from radio frequencies is reliable and effective. So when you are using these radio frequencies in order to harvest, there is a protocols, so such as time switching protocol and power splitting relaying protocol. So in normal relaying communication, when the relay is existing between the source and destination, in normal communication it has only two phases. One is receive the information from the source and transmit it back to the destination in the second phase. So when you are using energy harvesting in additionally, so we need to give separate slot for energy harvesting. So when you are using the time switching protocol for harvesting energy at the relay node, so you need to give some amount of time, alpha t amount of time as shown here for energy harvesting, and the remaining time for as usual information processing. So in usual information processing is in first phase it will receive the information, in second phase it will forward the. You have to choose the time switching parameter alpha very carefully so that there will be sufficient time for energy harvesting and sufficient time for information processing. If alpha equal to 0, that means there will be no time for energy harvesting. So, and it will be having the time for only information processing. So as relay doesn't have any energy, so it cannot give the required efficiency. Similarly, if alpha equal to 1, you have only slot for energy harvesting, there will be no slot for information processing. So you have to choose this alpha very carefully in order to get required efficiency of your energy harvesting node. Similarly, there is the second protocol, which is nothing but power splitting protocol. In power splitting protocol, when it will receive the information from the source, it will divide the total received power into two parts: beta power for energy harvesting and remaining part for information processing. In similar to the time switching protocol, we have to choose the power splitting parameter very carefully in order to maximize the throughput. If beta equal to 0, you don't have any slot for energy harvesting. If beta equal to 1, you don't have any slot for information reception, so you will lose the information. So you have to choose these protocol parameters very carefully in order to get your required throughput. So as we have said, our main focus is on two things. One is energy harvesting and second one is spectral efficient protocol. So one of the spectral efficient protocol we are focused is two-way relaying. So how this two-way relaying works, basically in conventional system, if you want information exchange between the two nodes, consider you have the node TA and TB. So it has a relay in between, so which will assist the communication between the TA and TB. So in order to fulfill the bidirectional information exchange, so it requires 4 time slot. In first time slot, TA will transmit the information to the relay. In the second time slot, relay will transmit the information to the B node. So in third time slot, B node will transmit the information to the relay. In fourth time slot, relay will transmit back the information to the TA node. So here, in order to exchange the information between TA and TB, it requires 4 time slot, which is in conventional. But in spectral efficient two-way relaying protocol, it requires only 2 time slot in order to do the information exchange between the TA and TB. So how it will do it? First slot, TA and TB will transmit the information to the relay. So at the relay, we have A plus B information. In second time slot, relay will transmit back the information to TA and TB. So both nodes will have A plus B. Then at the A node, so it already knows what's its own information. It will cancel out A from the A plus B, and it will get extract the information required, which is nothing but sent by B node. So similar process will happen at B node. So by this, we are able to achieve the information exchange between the two nodes in 2 time slot instead of 4 time slots. So we are saving the 2 extra time slots, which is used by another nodes. So by using this mechanism, we can improve the spectral efficiency. So the total talk we are dividing into 2 things. One is how we'll study how this energy harvesting is helpful for self-sustainable IoT solutions. In the second thing, we try to design these energy harvesting modules for self-sustainable IoT solutions. So first, we will investigate how this energy harvesting is really helpful for this self-sustainability. So in order to do that, we'll study the system. So first, we have considered two-way relaying network with energy harvesting node as a relay in between. So this energy harvesting relay node is nothing but the IoT node. So it assists the information exchange between the A node and B node. So I consider that A node has NA antennas and B node has NB antennas. So the communication will, as we have discussed, I have considered the time switching relaying protocol at the relay node. So in time switching relaying protocol, what we have 3 phases. In first phase, it will do the energy harvesting. In second phase, it will receive the information. In third phase, it will transmit back the information to the destination nodes. So here, I have considered the first phase. In first phase, the both nodes transmit the energy to the IoT relay node. In second phase, the IoT relay node receive the information from both the nodes by using the multiple access channel phase. In third phase, it will transmit back the information to the A node and B node by using the broadcast channel phase. So this is how the protocol at the relay node. So in first phase of alpha t time, the energy harvesting will happen, in which A or B node will transmit the energy to the relay. In the second phase, multiple access phase, both the nodes T and TB transmit the information to the relay. In third phase of broadcasting channel phase, the relay node transmit back the information to both TA and TB. So we have used the outage outage metric in order to analyze the performance of the network. So the outage is defined as of the SNR is below the threshold, then it will be in outage. And the PE here is nothing but activation threshold of your energy harvesting node. If your the received power PE is less than the PTH activation threshold power, the node will be in outage. That means it is not activated, so that it cannot support the communication. So whenever the received power is greater than the threshold power of your node, it will be activated. Then it will do the processing. Then we will analyze whether this SNR is below the threshold or not. So by using the outage, we have analyzed the diversity of the system. So the diversity is proved that it is depend upon number of antennas at the A node and number of antennas at the B node, which is similar to the conventional system. So by this observation, we can see that in terms of performance, we are not losing when you are employing the energy harvesting at the relay. This is very important point. So when you are giving the additional phase for energy harvesting, we are not losing in terms of diversity basically. And throughput is defined as 1 minus P outage, which is nothing but success rate into how much time you are sending the information into the corresponding rate of transmission. So we have all, as we have discussed, if alpha equal to 0, there will be no energy harvesting time. If alpha equal to 1, we have only time for energy harvesting. There will be no information processing time. So we have to select alpha, the time switching parameter, such that it will maximize the throughput of our system. So we have, interestingly, we have observed that this throughput is nothing but concave function of your time switching parameter. That means if you select optimum time switching parameter, you are able to maximize your throughput. So if you can see that when alpha equal to 0, your throughput is 0 because there is no time for energy harvesting, so that there is no energy available at your IoT node in order to support the information transmission. Similarly, if alpha equal to 1, you are totally dedicating your time for only energy harvesting. There is no information reception or information forwarding. So you have to select alpha such that you are able to maximize your throughput. So similarly, you can see that as number of antennas is increasing, your throughput is increasing, which is normally you can see in any MIMO system. But the concave behavior is a very important point in order to maximize your throughput. So what we have done? So based on our channel parameter, we are able to derive, and we have seen that throughput is maximum instead of taking the constant TSR parameter. If you take the constant TSR parameter alpha equal to 0.4, you can observe that your throughput is very low. In blue curve shows that the throughput is lower, and the black curve shows that when you are using the optimum time switching parameter, your throughput is able to be maximized. Right. So from this observation, we have able to see, from this study, we have observed that the diversity is unaffected even we are employing the energy harvesting, and it is observed that the throughput can be maximized by selecting the optimum TSR parameter. These findings are reported to the IEEE Transactions on Communication, and it is published. And we are also derived the closed form expression for this optimum TSR parameter based on your channel conditions, so that we are in predefined TSR parameter can be fixed at your IoT node, so that it will operate at that point and it will maximize your throughput. So that is the first problem we have investigated for IoT networks. So second thing is when we are using the IoT network in cognitive scenario. So what is meant by cognitive radio? Cognitive radio is used to improve the spectral utilization to meet the exponentially growing requirement of your wireless system. So how this cognitive radio works? Basically, we have the licensed users and the unlicensed users. So the licensed users called primary network, and the unlicensed users are called secondary network users. So these secondary unlicensed users will operate along with this primary network in the three manners. One is underlay cognitive radio, the second is overlay cognitive radio, and the other one is interwave cognitive radio scenario. So in underlay cognitive radio scenario, how it works basically? So the both this primary network and secondary network works simultaneously at same time. But the secondary network has the interference temperature limit, which is nothing but IP. So this limitation is imposed on the secondary network so that it will not disturb the primary network beyond the limit. And the second scenario is overlay cognitive radio scenario, in which secondary networks assist the primary network communication. So the secondary network will receive both the information from the primary and secondary, and it will transmit the information to the primary destination as well as secondary, so that it will work along with this primary network. And the third one is interwave. It is nothing but switch on, switch off. When the primary network is off, it will work. When the primary network is on, it will off. So this is the three type of scenario in which the secondary network will work along with this primary network in order to utilize the spectrum in more efficient manner. So this is the network which we have considered. So we have considered the underlay scenario, so in which we have the interference temperature limit on the secondary nodes. That means the secondary nodes cannot transmit the power beyond a certain limit of IP. So as usual, we have considered the PSR, power splitting relaying protocol. So in power splitting relaying protocol, we have only two phases. One is in first phase, the total received power will be divided for energy harvesting as well as information processing. In the second phase, the relay will transmit back the information to both the nodes based on the harvested power. So here you can see that in two-way relaying networks, both the nodes transmit the information at same time. So we have fixed the limit on the transmitted power of PA and the transmitted power of PB. So this transmitted power PA is nothing but 1 minus nu into IP by GA square, the channel. And the second power which is transmitted by TB is nothing but nu into IP by GB square. So if you see the received power or the power limitation at PR, received power at PR is nothing but square root of PA into GA into XA, whatever the information transmitted. And the second is square root of PB into GB into XB. So if you calculate the power, it will be turned out to be IP, which is the limitation imposed on the secondary networks by the primary receiver. So that means what you are doing, you are not going beyond the limit of the primary threshold. So here in this scenario, we have two parameters. One is nothing but PSR parameter, another is nothing but the optimization of interference apportioning parameter. So you have to set optimize two parameters. One is energy harvesting parameter, another one is your interference apportioning parameter. So what we observe, instead of taking the fixed parameter values, if you are able to optimize this parameter very carefully, you are able to achieve the better throughput. So here you can see that the blue lines indicates the lower throughput scenario, which is nothing but fixed TSR, fixed PSR and interference apportioning parameter. And the red line shows that when you are able to optimize these two parameters, you are able to improve your throughput. So in this problem, we have able to get the closed form expression for both PSR parameter and ITAP parameter based on your channel conditions. So if you are able to use this optimized PSR and ITAP parameter, you are able to maximize your throughput. So these findings are reported to the IEEE communications letters. So it shows that in cognitive radio scenario also, if you are using the energy harvesting protocol by using the RF energy, you are able to improve your throughput. So in third scenario, what we have seen in previous two scenarios is we are only depend upon your harvested energy. But we have observed that the harvested energy from the RF energy is very small. In order to get information transmission, we have to wait for long time for energy harvesting. So if there is a quality of constraint is there on the information in the network, so it cannot meet the service requirements if you are only depend upon harvested energy. So we come up with the plan that why don't we use hybrid energy harvesting relay? That means the relay has some battery energy and we are using the harvested energy to maximize the lifetime of your IoT node. So that means we are using the battery energy whenever is required. We are not using the battery energy in all times. We are using whenever the harvest energy is very low, we use the battery energy. Otherwise, we don't use, so that we can maximize the lifetime of your battery energy. So in this network, so we are using the time switching protocol. So in time switching relaying protocol, it has 3 phases as we have discussed. First phase is energy harvesting. Second phase is multiple access channel protocol, and third one is broadcasting channel. So this is how it works. So in first phase, we are doing the energy harvesting. In second phase, we are receiving the information. In third phase, we are broadcasting the information. So here, if you see that how this hybrid relay works, basically alpha t time, it will harvest the energy. So this harvested energy is compensated to the battery energy by using the battery energy control unit. So this both combined harvested energy plus battery energy will be available at the relay. So here, this battery energy control unit extract very small amount of energy based on your harvest energy. If your harvest energy is sufficient, it will not extract any energy from the battery. If your harvest energy is low, then only it will extract the energy from the battery. So this is what happens. After that, 1 minus alpha t by 2 time, the relay will receive the information, which is nothing but the second block which is showing. It will process the information. In third phase, the relay will use this combined energy in order to transmit this processed information to the both the nodes, so that your battery energy will be extracted battery energy very low. So this is the throughput of your two-way relaying system, which we have already seen. That is nothing but success rate, success data into the how much time we are transmitting that information and the transmission rate. So we have observed that the throughput behaves in concave manner, and if you are able to optimize your time switching relaying parameter, we are able to maximize your throughput. But in first scenario, if you see, when alpha equal to 0, we are getting the 0 throughput, but we are not getting 0 throughput here when alpha equal to 0. Why? Because we have small amount of battery energy. So if you see, if EB equal to 0, your throughput is 0 because there is no battery energy, there is no harvested energy. But if you see EB equal to 0.5, 1 and 2, the left side curve, when alpha equal to 0, we are having some throughput, because even though there is no time for energy harvesting, we have additional battery energy in backup to the harvest energy, which will enable us to process the information and forward the information. So in the second curve, you can see that when you are taking the fixed time switching parameter value, either alpha equal to 0 and alpha equal to 0.5. So red curve shows that alpha equal to 0.5, and light blue curve shows that alpha equal to 0. So in these two cases, when you are taking the fixed PSR parameter, we are getting the lower throughput. But when you are optimize your TSR parameter, the blue and green line shows that when you are optimizing your TSR parameter, you are able to maximize your throughput. In this scenario, we have considered two channel conditions. One is statistical channel state information, and another one is instantaneous channel state information. When you have the statistical channel information, you can observe that we are consuming more energy. So you can say that you can take any row. So you can take that when your consumption of energy is 1 joule, you are getting the 0.32 throughput. But when you have has instantaneous channel information, we are consuming the 0.28 energy, sorry, 0.32 energy, and we are getting the higher throughput 0.62, right? So what we are observed, when you have statistical channel information, we are consuming more energy, but we are getting the less throughput. But when you are having instantaneous channel information, we are consuming the less energy, but we are getting the more throughput. So this instantaneous channel information will help and improve the throughput very drastically. But challenging is getting this instantaneous channel information at every time instant of coherence time. So further, so we have seen that throughput improvement when you have the statistical and instantaneous channel conditions. The second one is energy consumption for the target throughput conditions. So in quality of service constraints, so it has some constraints such as we need the throughput should not go below this. So when you have this target throughput conditions, so we have analyzed how this energy consumption behaves. It is observed that this energy consumption is showing the convex behavior with the time switching parameter. And if you are able to select or operate your IoT node at this optimum time switching parameter, you are able to achieve the lowest energy consumption for the target throughput requirement. And we are able to derive the closed form expression for this time switching parameter based on your channel values. So, and this is when we have the statistical channel knowledge, the left side graph. So in right side graph, it shows that as compared to your statistical channel information, when we have your instantaneous channel information, we are getting the lower energy consumption. The red bar shows that when you have the channels statistical channel knowledge, and the green bar shows when you have the instantaneous channel knowledge. So this instantaneous channel knowledge will help us for the dynamic decisions. If the channel is good, it will transmit. If channel is not good, it doesn't transmit. So that you are able to conserve your energy. So this energy consumption minimization will help you to maximize your lifetime of your nodes. So in this scenario, we are able to get the closed form expression for your optimum TSR or PSR parameter based on your channel conditions. And the second one is we have observed that when you have the instantaneous channel information, we are getting the lower energy consumption and the higher throughputs. So these findings are reported and filed in for US patent application, and it is also reported in IEEE System Journal and IEEE Transaction Communication. So by these three scenarios, we are able to see that how this energy harvesting by using the radio frequency will help us to maximize the lifetime of your node and to maximize your throughput. So if you have any doubts, we'll take 5 minutes break. So to get any doubts in this. So further, we will see how this energy harvesting can be used to in our applications.
Hello.
Yes.
Hi, Dr.
Ye-
Sudhakar.
Yes,
Do
ma'am.
do you require a gap of 5-10 minutes now?
Yes, yes. I'm giving the 5 minutes gap just to see
Okay.
any doubts or
No. I
proceed.
think better you proceed now, and all the queries will be
Yes, yes,
added.
yes. So then it is fine. So I'll
Yes,
proceed with
please,
it. Yeah.
please. Okay.
So we have observed that the energy harvesting can be used to maximize the lifetime of your node and maximize your throughput. So how this energy harvesting IoT nodes can be used for your smart applications. So when you see the applications of this IoT, it has the various applications starting from agriculture, smart cities, water management, healthcare, etc. So if you see any one scenario, so in agriculture you need to collect different parameters such as soil strength, moisture, temperature, and rain detection, and all these things. So based on the parameters, the IoT node will transmit these parameters to the central node. From the central node, the required action will be taken, whether you need to start the motor or whether you need to give any parameters for the improvement of productivity. So when you are using this energy harvesting IoT node, so it has the energy constraint. When there is a constraint on energy consumption, we need to make the node intelligent so that it can make the context aware event detection and machine learning based decision making and etc. So before going further, so I'll just introduce what is IoT. IoT is nothing but we have sensor node. Sensor node consists of this sensor module, actuator module, microcontroller, and communication module. So it will sense the parameter by using the sensor modules. The microcontroller transmit these sensed parameters by using the communication module to the gateway. So the gateway is connected to the internet. Internet is connected to the cloud. So these parameters will be monitored from the cloud scenario. So in cloud, it will do the different analytics. So based on this data analytics, it will make the actuation command from the central control room. So this actuation command will be implemented at your sensor node back by using the actuator module. So we'll discuss one by one. So different modules, sensor modules. Sensor modules basically senses the ambient condition and transfer this information by using this microcontroller. So there are different sensors based on your applications. So we have tested this smart agriculture applications where we have used your rain sensor, so which is nothing but second column, second row, and moisture sensor and humidity sensor, nothing but third row and fourth column. And so based on similarly, so the last one, soil moisture sensor, which is nothing but last one. So last row, last column. So based on your application, we'll use the different sensors to get different parameter values. So the other module is actuator module. So based on the command received from the central command control room, so it will implement the required actuation. So basically, there are different type of actuators such as mechanical, hydraulic, pneumatic, such this type of actuators. So based on your application, you'll use the different actuators. So we have used the motor, which is nothing but mechanical actuator. So these are the different type of microcontrollers which is used at the sensor node. So this controller will accommodate different sensors and communication modules. So here there are different type of microcontrollers such as Arduino Uno, Raspberry Pi, and MCU and Intel Galileo. But mostly we use Raspberry Pi. So when Arduino Uno is economical, but it doesn't have communication module, so we need to use external communication module. But Raspberry has its own communication module, and it is basically used in most of the applications. So this sensor node will communicate to other sensor node or to the gateway by using these type of protocols. There are different types based on the range. So the protocols are Sigfox, LoRa, and cellular, which is used for low power and wide area network communication protocol. And short range communication protocols are Zigbee, RFID, and all these things. So Zigbee is these are the description. Zigbee is used basically for communication. LoRa is used for long. So mostly we prefer LoRa type of communication scenario. And these are the different protocols which used for sensor. So this, when you see the commercial aspects of this IoT, so it has 40% in industry 4.0, and it has 30% role in this healthcare, and 8% retail, and 7% in security. So which shows that it has a bigger role in the coming decade to play. So we have said that when you are using this energy, billions and billions of IoT modules, so replacement of battery or recharging of battery is very difficult. So we are, as we have discussed, we are trying to use this energy harvesting at this IoT node. So we have proposed that instead of using only the RF based energy harvesting, we use the hybrid scenario where we use the RF based energy harvesting as well as solar if it is outdoor. If it is indoor, we use the electromechanical energy harvesting. So in addition to your battery module, so based on this battery and the harvest energy, your IoT module will operate and it will senses the different parameter and it will transmit to the your gateway. And in order to make self-sustainable, we propose the MAC protocol, which is energy efficient and intelligent decision making at your IoT node. So once we have make this prototype ready, so we'll deploy it in the real-time scenario, collect the data and verify its performance. Based on this performance requirements, again we'll redesign it and we'll go for the design improvement. So this is one of the application which we have tried it at IIT Jammu. So we have used for precision agriculture. So where you will collect different parameters such as soil moisture, humidity, temperature, and all this data, and it will be transmitted to the central control room and to the cloud. So and the remote locations, from the remote location, we can able to monitor different type of parameters. Based on the parameters, we'll take the decision when to on the motor, when to off the motor, and all these things. So this is the CC which shows here in red line is our central command room, and the nodes are deployed in different places, which is N1 to N9. So from these different node places, we'll collect the parameters, and from the central room, we'll operate when to on the motor, when to off the motor, or we can pre-design that if your moisture level is low, so below the threshold value, so the motor will automatically activate, and when the it will go above the point, it will automatically off, like that. So we need to expand it to the bigger scenario. So this is the display of different parameters from the command control room. So this is we use the ThinkSpeak network. So and we have used the Blink app to monitor it in mobile, and ThinkSpeak to monitor in our desktop from the central command room. So how it is relevant to your Indian scenario? So agriculture is main industry in India. So if you are using this smart agriculture practices, it will ensure the food security in future. So further applications are smart water management, healthcare, and transportation, which will improve the standard of living. But also it is required when to the current scenario of limited resources availability. So with the existence of this IoT, artificial intelligence, and smart solutions, it has the open up the very big business opportunities. So if you see this especially for this RF based energy harvesting, there is only some companies which are working outside India. So in USA, the forecast is working. So where they are designing this RF based small modules for this glowing the light RFID detection and all these things. And the Innovation Germany company, so which is working for this communication module of RF based. So and third one is Dyson, which is based on the London, which is try to replace our batteries by using this harvested energy. So with this basic idea is use this RF modules, RF energy harvesting modules to operate your mobiles. So in India, there is no companies working on it. So we're trying to build our own modules to make it self-sustainable IoT solutions. So thank you. So these results are as we have discussed. So this RF-based energy harvesting is applied for US patent, and these are the different type of publications. If you have any doubts, you can ask.
Hello. Hi, Dr.
Yes, Taimur.
Sudhakar.
Yes, sir.
Uh,
Yes.
your talk is over.
Yes, yes. It is all.
Okay. Then there is a query from the participants.
Yes, yes.
Uh, in time splitting techniques, the objective function is concave. Then
Hmm.
kindly suggest the method to solve the function to get the optimal result for.
Yes, I'll just discuss. Yes. So here you can see that the throughput shows that concave behavior with respect to your time switching parameter. So here we are using the only one IoT module. So after getting the throughput, which is in terms of outage, so we have used that ISNR outage approximation, which is come in terms of linear form of in terms of alpha. So if polynomial form of alpha, so if everything is polynomial, we can get the optimum DSR parameter just by using the double differentiate. So in double differentiate, if you differentiate it and make it 0, so by using this, you can get the optimum time switching parameter, which will maximize your throughput. So this is the method. But when you are having multiple nodes, so instead of single node, consider you have the different nodes and the different time allocation parameters will be there. In that scenario, you need to use the optimization techniques such as semi-definite realization and all these things, convex optimization.
Okay.
Yeah.
With this, I must say final thank you for you.
Thank you. Thank you. So
For
thank you for
for,
NIT Silchar for
for
giving this
accepting
opportunity.
for
Yeah.
accepting our invitation and for delivering a talk in this ongoing 1 week
Yes.
FD on ICT for smart city applications. In addition, I would like to invite you for the valedictory session to be conducted on 15th January at 3:30 p.m. Okay.
Yes. Thank you. Thank you. Yeah.
Have a nice day. Bye.
Thank you. Thank you for NIT Silchar for giving the opportunity. So I look forward to the validatory session. Thank you
So
so much, sir. Yeah.
now for the participants, like we will take lunch break up to 1:30, and the third session of the day will start at 1:30 p.m. Okay, bye.
Yeah. Thank you, sir. Thank you, sir. See.
See
Yeah.
you all at 1:30.